Welcome everyone to this explainer. Today we're going deep underground to uncover the invisible physics that dictate structural foundation design. You know, every massive skyscraper, every heavy-duty structure you see relies absolutely on a solid foundation to keep it standing. And a lot of the time, that foundation is a massive concrete slab known as a raft. But a raft foundation isn't just some simple block of poured concrete. It is a highly engineered battleground of clashing forces, invisible stress lines, and incredibly specific steel placement. So if you've ever wondered how civil and structural engineers ensure a massive building doesn't just sink into the earth or literally snap its own foundation in half, you are in the exact right place.
So let's start with the puzzle that keeps engineers up at night. Where do bending moment and shear force actually peak in a raft? These are two incredibly antagonistic structural forces that are constantly trying to tear a foundation apart. Do they hit the hardest directly under the immense weight of a column, or do they peak out in the middle of the slab between the columns? Figuring out exactly where these forces reach their absolute maximum limits is the core of structural analysis. It literally dictates every single decision made on a construction site.
Which leads us to our next critical question. Why do top and bottom rebars, the steel reinforcement bars hidden inside the concrete, need entirely different lapping zones? When you're building a massive raft, you can't just use one continuous, endless piece of steel. Bars have to be cut and spliced together. But joining them in the wrong place, that can lead to catastrophic structural failure. Today, we're setting up this exact practical engineering problem, and by the end, you'll know exactly how to solve it.
Okay, let's dive into this. Here is our roadmap for how we'll travel from invisible forces to real-world field application. We're covering foundation forces, bending moment and rebar, surviving shear force, the strict rebar lapping rules, top versus bottom lapping zones, and finally, an engineering reality check.
First up, Section 1, Foundation Forces, the Invisible Battle. Let's move to how this builds. I really want you to think of a raft foundation not as a static resting object, but as a battleground taking place 24/7. First, in Step 1, the columns of the building are driving immense, concentrated downward loads straight into the raft. But remember Isaac Newton? For every action, there's an equal and opposite reaction. That brings us to Step 2. The earth below isn't just taking the hit. The soil is actually pushing back up against the entire bottom of the raft with upward contact pressure. So you've got columns punching down and soil pushing up. Step 3 is the result of this massive squeeze, the creation of intense internal stresses known as bending moment and shear force. The raft is literally caught in a giant vise.
Moving on to Section 2, bending moment and rebar. We'll use the ruler analogy for this one.
Because of this intense dual-sided pressure, the concrete raft is forced to physically bend. We call this bending moment, and it's the main reason we need to pack our concrete full of steel reinforcement. To really visualize this, think of the ruler analogy. Just imagine holding a plastic ruler horizontally. If you push down on the middle while supporting the ends, the ruler sags down, right? The top surface compresses, but the bottom surface stretches out. It goes into tension. Now, concrete is incredibly strong when you compress it, but it's terribly weak when stretched or pulled in tension. In a raft foundation, directly over the columns, the slab tends to bend upwards in what we call a hogging moment, creating high tension on the top surface. Between the columns, where the soil is pushing up, it bends downwards in a sagging moment, creating high tension on the bottom surface.
And this brilliantly illustrates exactly how we solve the bending problem. Because concrete hates tension, we have to put our steel exactly where that tension peaks. Over the columns, we have negative bending moment, which creates tension at the top of the slab. So, top rebar is the absolute hero here, doing the heavy lifting to keep the concrete from cracking wide open. Meanwhile, between the columns, we have positive bending moment, creating bottom tension. Here, bottom rebar is absolutely critical. The steel is mapped perfectly to the invisible stress envelope.
Let's jump into Section 3, Surviving Shear Force, the Cutting Edge.
Now, bending isn't the only structural villain we're dealing with. If bending moment wants to stretch the slab, shear force wants to cleanly slice right through it. This happens right where the load is transferred. And the most dangerous type, punching shear. Think of a stiletto heel stepping onto a soft wooden floor. The immense concentrated load of a column wants to punch a hole straight down through the concrete slab, taking a cone-shaped chunk of the foundation with it. To prevent this, engineers define a critical perimeter entirely around the face of the column to check if the concrete is thick enough and reinforced enough to stop the column from just punching straight through to the dirt below.
You can see the stark contrast in these behaviors. You've got one-way shear where the raft attempts to fail along a straight line, almost like a strip of paper being snipped by scissors across its width.
But then you have the much more critical punching shear, where the column punches down in a cone shape. Because of this, the zone immediately surrounding the column face is incredibly dangerous and requires meticulous shear design and heavily concentrated reinforcement.
Let's move into Section 4, the rules of rebar lapping, connecting the steel.
Okay, we're taking this theoretical physics into the physical reality of a job site. Steel bars come from the factory in standard lengths, right? So to span a massive sprawling foundation, they have to be joined together. And how we connect this steel is quite literally a make-or-break detail. This connection is formally known as a lap splice. It involves overlapping two reinforcement bars for a highly calculated length. The goal here is to safely transfer the structural forces, whether that's tension or compression, from one bar into the concrete and then seamlessly into the next bar. It's exactly like a baton pass in a relay race, but dealing with hundreds of thousands of pounds of force.
Creating that lap splice is vastly more complex than just tying two metal sticks together with some wire. Engineers have to calculate the exact lap length and development length based on the specific bar diameter. They factor in concrete and steel grades and specific bond conditions. All of this must strictly adhere to complex code requirements. Furthermore, you can't just splice all your bars in the exact same line. You have to stagger laps to avoid creating a weak cross-section and to prevent concrete congestion. If the rebar gets too thick and congested to pour concrete properly, we actually have to ditch lapping altogether and use threaded mechanical couplers.
Section 5, lapping zones, top versus bottom or dodging the stress.
So, the crucial point is, where do we actually place these splices? It's all about dodging the stress. We have to map our physical rebar cuts directly to the bending moment physics we talked about earlier. The golden rule of detailing is this: never ever lap in a maximum tension zone. A lap splice, no matter how perfectly designed, is always a potential weak link in your structural chain. You absolutely want to place your splices in the low-stress regions. We want continuous, unbroken steel handling the highest tensile stresses to ensure our structural continuity remains completely uncompromised.
Let's see how this rule plays out in our Raft foundation. For bottom rebar laps, remember that bottom tension is highest between the columns due to sagging moment. Therefore, we avoid lapping there. We prefer to place bottom lap splices near the columns, firmly in the low-stress zone for the bottom steel. Top rebar laps follow the exact opposite logic. Top tension is highest over the columns due to hogging moment, so we avoid splicing top bars directly over a column. Instead, we place top splices between the columns, where the top surface stress drops way down.
Let's wrap it up with Section 6, an engineering reality check, beyond the rules.
Now, what's really interesting about this slide is that it shows us the danger of blind trust. If you just take those simplified rules of thumb to a job site, you are asking for trouble. The harsh truth is, fixed rules are a myth. The whole laptop bars here, lap bottom bars there concept is a handy generalization, but in a real-world raft, bending moment diagrams are rarely perfectly uniform. You have varying loads, like a super heavy elevator core column right next to a lighter perimeter column. You have edge conditions, openings for pits, retaining walls, uneven soil pressure. All of these dynamic variables shift the moment distribution, meaning those maximum tension zones can migrate to totally unexpected places.
To help you navigate this reality, here is your ultimate cheat sheet summarizing everything we've covered today. Over the column, the behavior is negative bending moment, so the main reinforcement is top rebar. Your lap rule? Actively find the low tension zone for that specific top steel. Between the columns, you have positive bending moment, requiring bottom rebar. Again, you must find the low tension zone in the bottom envelope. And near the column face, that's your high punching shear zone. That area is absolutely critical for shear design, and you must aggressively avoid placing lap splices there if at all possible.
I want to leave you with this thought. Understanding the stress envelope is what makes a real engineer. Blindly following detailing rules is what causes failures. You really can't just assume a lap length of 40 or 50 times the bar diameter will work everywhere just because it's an industry habit. True engineering practice requires looking at the actual bending moment envelope generated by the structural analysis, applying the applicable codes, and strategically placing your steel exactly where the math tells you it belongs. Once you understand where the loads go and how the stress flows, understanding why the reinforcement is placed there becomes second nature. Thank you for joining me in uncovering the hidden physics of Raft foundations on this explainer. Keep asking questions, keep studying those stress envelopes, and I'll see you next time.